Next up is Tim Woolery of ACT has been protecting the world's infrastructure since 1976 when they began producing silane concrete, water repellents in Oklahoma. Before that, Tim spent 30 years in the solvent-based coating business. And for me, and I think a lot of people, Tim is Professor Silane.
Good morning. It's kind of like having a family reunion. We're all back here in face-to-face, so it's been pretty nice to see all you people. So welcome. Wow, you guys are getting a blast of water repellents today, though. That's pretty exciting. So we've talked a lot about what, can you hear me all right? We've talked a lot about water repellents today, and that, John talked about, this is what we need to do to protect your bridge. You need to do something. And so water repellents are one of the easiest things you can do. Maintenance crews can do it. So what I'm going to talk about is just silanes in general. And so we'll go through, we'll talk about, what concrete damage, which you've just seen a lot of, what silanes are, how much they've been tested. Obviously, I need to add another university to my slide on how many universities are currently studying silanes, because there's a bunch. We'll go through the application techniques, writing specifications, which I think is really important for the states to write the proper specification. And then we'll go through the cost of what it actually costs to put silanes down, and we'll have some fun. Obviously, we've all talked about water being what's the real problem here: de-icing, salts in water, freeze-thaw damage. You've seen all these slides before: salt, scaling, cracking. Rebar corrosion is one that I really see a lot as I travel the country now. It's not so much, we're doing a great job of taking care of our bridge decks, but it's our substructures. I mean, I see this all the time. And so these kind of things can be prevented and slowed down if we just do that work ahead of time. Alkali-silica reaction is something that, I think we discovered back in our country about in the 30s. It is progressing rapidly across the country. We just did a big presentation here in Arkansas about ASR because they're having a lot of problem on their roadways with ASR right now. So for those of you who are not that familiar about what ASR is, that alkali-silica reaction, it forms this gel in the concrete, and it expands that concrete to where it can bust the concrete. This is a great picture. This is actually an abutment up in Maine. And this is a problem in a lot of these states. It just exudes this gel out of there. It's map cracking. It's a real problem. So for mitigation for this, a little bit of a rabbit trail, it's either you have to change your aggregates, you need to change your concrete mix design. John talked about the SCMs earlier, or CSMs, I guess. So you either need to do that or you need to put water repellents. You have to keep one of those things out of there. Obviously, dealing with aggregates, you kind of get what you get. I mean, how much testing can you do? How much time do you have to do a bunch of testing on your aggregates? So now you got to work on your concrete mix design, more fly ash, whatever it takes to put in there, or you use water repellents to keep the water out. Talked about silanes earlier in the previous presentations. They are a penetrating sealer. They form, and this is a great picture right here. So this is a picture that shows what the untreated concrete looks like, what a film former looks like in that concrete, and you can see how it's a poor blocker. It just coats that whole concrete, and then what silanes do. And silanes react with the silica in that concrete, and they make the concrete hydrophobic. They allow vapor permeability, but they change that surface tension of the concrete so the water can't penetrate in those pores. This is loose sand. If you walk by my booth, and you'll see this loose sand, and so you can treat just loose sand with silane, and that water will bead on there until somebody walks by and sticks their finger in it. But that's what happens. It forms that chemical bond with the concrete, keeps the water out. They talked about the contact angle helping with water repellency. This just kind of shows that. This is a block that's been dipped in silane, and you can see the middle of it looks wet, but the water is not penetrating from the top. And that's what you want. You want bridge decks are not going to bead water. It's just not going to happen. But what you're trying to do is keep as much of that water out of that bridge deck as you can, and that's what these kind of penetrating sealers do. There's a whole lot of silanes out there on the market. There's a lot of people selling silanes. And so they all work, okay? They all work. The difference in most of them is in dry time. So you can see these big words out here. They're all alkyl tricarboxysilanes. There's isobutyl-trimethoxys and isobutyl-triethoxys, and then there's normal octyl. And so all these are is the length of chain of that molecular structure of the silane. They all work. The difference is in the dry time. So if you get down to these isooctyl trimethoxys, you might be on that bridge deck for 6 or 8 hours waiting for that stuff to dry. We just talked about lane closures. If you use the isobutyl trimethoxys, you're going to be off that bridge deck in 30 minutes, depending on time and temperature. So it's about dry time. I was just on the Peace Bridge in New York a week ago. That bridge has cameras all over it. They did a dry time study on silanes. They put one on there, it took 21 and a half hours. They put another one on and it took an hour and a half to drive. Which one do you suppose they used? I mean, you can't keep a bridge closed, especially, you know, an international bridge. You cannot keep those lanes closed. Well, you can now because of COVID, but prior to that, you couldn't keep those bridges closed. So lane closures are important, and you need to get those things open as fast as you can. So that's part of that when you start talking about developing a water repellent program. Is it easy for my crews to do? How fast is it going to close my bridges? That's what you need to be thinking about. So this kind of shows that molecule, the silane molecule there on the left. It's very small. It's one of the smallest molecular structures these things are, so they penetrate deeply. And then you have this siloxane molecule that just shows how big it is compared to the silane, and it's more of a surface type of a treatment. So if you're using siloxanes, which they use on buildings because they want to see them bead water, that's an important thing, but we don't care about water beading, we care about keeping the water out of the concrete. Talk about testing. These are some of the DOT testing that's been going on for years. Oklahoma started it. That was finished in 1986. It was started in 1976. So silanes have been tested by more DOTs than probably anything. University studies, Purdue's doing theirs, Oklahoma State University constantly is doing it. Michigan Tech just finished one, Michigan State, and I need to add Kansas to that. So, I mean, they're constantly being studied, and I think the deal is kind of like they were talking earlier, is it snake oil? Do I know it's there? How do I know it's there? How long does it work? So they just constantly keep doing these studies over and over. Here's one from 1985 by Wisjani Elsner. 4 to 8 week salt ponding test, kept out, 97% of the water out of that, or the chlorides, 0 rebar rust. So this is what that looks like. This is from the Wisjani Elsner test. It shows with silane, there's no rebar corrosion after 48 weeks of salt ponding. Without silane, there's rebar corrosion. So they work. They've been tested, they work. And they're inexpensive. Some of those performance criteria that they were talking about earlier, these are some of the tests that most of the DOTs run. Question I always have is, okay, if I require it to be 90% of moisture absorption or reduction in moisture absorption, does that mean that 89 doesn't work? So when we write these specifications, we kind of have to be careful of that because you can paint yourself into a box and all of a sudden, well, I got to have 92% moisture reduction. Well, does that mean that if every silane that comes in at 91 doesn't work? So we kind of write these specifications and we need to be careful about how we write those things. So this kind of just gives you an example. This is called a rylum tube, if you've never seen a rylum tube in there. And this is how they use this in parking garages a lot to determine moisture absorption of concrete. So you can see the one on my right, because it's going through that concrete. Well, it just shows you how that if you can't see it on there, it doesn't change the appearance of the concrete, doesn't change the skid resistance, but there it is, it's drinking water in one and not the other one. One of the biggest questions is how long do silanes last? So this is a study done by Oklahoma State University. They took 60 bridges, they pulled 360 cores, and the results were that in bridges that were, 12 years old, still showed the presence and the activity of silanes for 12 years. Bridges that were 15 years, 66% of them still showed silane, and the bridges that were 17 to 20 years old showed it at 21%. So, how long do silanes last? Obviously, they can last up to 12 years. Oklahoma uses a 40% silane. A lot of the states are going to 100% silanes, and I think most people would recommend that now just because of the cost. I mean, when you get down to the square foot per gallon, it's just cheaper to use the hundreds. We'll talk about that in a minute. Surface preparation for applying silanes. A lot of places just sweep it, some power wash it, some shot blast it. Oklahoma, we shot blast it. So this shows just for those of you who aren't aware of shot blasting, this is what they do in Oklahoma. They build a bridge, They let it sit for a year, then they come back and they shot blast it, and then they apply silanes, and then they also start fixing cracks at the same time. Oklahoma is the only state I know that does shot blasting prior to silane. This is a bridge in Arkansas. So this is, and you'll notice on this that there's a blue tint to that silane. A lot of places do. We put a dye in there so that when the inspectors come by, they can say, it looks blue, currently it's pink, but they can say, oh, okay, I can see that bridge has been treated. So once you saw this application a minute ago with spray bars, this is just a walk behind spray bar. It's inexpensive to put a maintenance crew to doing this type of work. It's pretty simple. That's up around Bentonville. So truck mounted unit, this is a guy up in Illinois. This is one that, this was a truck that was built by Indiana DOT for their bridges. There's a problem with this one. This is a picture of how not to do it. If you'll notice, that spray bar is way off the ground. That spray bar needs to be about 4 inches off the ground. This is good for silane salespeople, bad for bridge decks. Okay? This is not how to do it. If you're going to put silane down, get it down to the ground so that it goes into the surface of the concrete, and then hand spraying. So, writing specifications. When you're writing your specification for silane, I want you to get what you pay for. A silane sales guy can walk in there and go, mine goes 400 square feet per gallon. Then the next guy that walks in there says, mine will go 600 square feet per gallon. Well, they will, but you don't get what you pay for that way. So all the testing, most of the testing has been done on silanes is about 11 grams per square foot of silane. And to get that 11 grams per square foot of silane, it takes about 60 square feet per gallon for 20% silanes, 125 square feet for 40s, and 300 square feet per gallon for hundreds. If you write your specification that says, I want this, we're going to use 100% silanes, I want my square footage to be 250 square feet per gallon, then every contractor does it the same. And you don't get cheated, and you get what you pay for, and then you know the performance of that is going to be good. So get what you pay for when you write a specification. A lot of times those get written as, oh, do it to manufacturer's recommended application rate, right? We can write whatever we want on that document. So make sure you get what you want when you do that, when you write that specification. Weather does matter. In a rain event, you want to at least wait 24 to 48 hours, depending on how much rain there is. Rain after silane, that doesn't hurt it. It helps with that reaction process, actually. We talked about cost earlier. So most people are not using 20% silanes. They used to be very common years ago because silanes were very expensive. So if you applied it at 60 square feet per gallon, 11 grams, $15 a gallon, it costs you 25 cents per square feet for that. Same math scenario here with 40% silanes at $20 a gallon. It's about 16 cents a foot. Here's where you make money for you guys, and that's where if you're using 100% silane at 300 square feet per gallon, it's down to 12 cents a foot. It's pretty inexpensive. That if it's going to last 10 years, it's a pretty inexpensive process for you to do. It's low tech. It's easy for maintenance crews to do it. And yeah, you should retreat them every 6 to 10 years. It's just good practice. You're getting more cracks, and it's just good to be on your bridges. So 100% silane. So why does it get cheaper as it gets up? The manufacturers don't have to touch it. When they're importing these 100% silanes, you're buying that raw material that the 40s and 20s are made out of. So anytime a manufacturer has to touch that, if he takes 100% silane and reduces it down to a 40%, he has to touch it. He has to put solvent in it, add all these things to it, repackage it in drums or totes or fives or whatever, and then re-quality control it before it ever gets shipped out. So in the manufacturing process, every time you touch something, that cost goes up. Even though you're reducing the amount of silane, the cost can go up per square foot because we're just touching it. There's a typical kind of bridge in Oklahoma. It was about 150 feet by 38 feet, 5,700 square feet of bridge deck. When I made this slide years ago, it was about $140 a foot to build a bridge. I don't think it costs that today. I'm sure it's a little more than that. That 5,700 square feet takes 45 gallons of silane. It costs $800,000 to build that bridge and $912 to protect it. It's a pretty inexpensive investment. If you had an $800,000 car, would you change the oil in it if it cost you $912? Probably, right? Silanes have been tested by everybody on the planet for years. It's never too late to start. Even if you have chlorides already in your bridge stick, it's not too late to start a silane program. It's also not an either-or thing. You can put silanes down and you can put healer sealers over the top of them. And that is good for that. I mean, you change that vapor permeability, but you have a belt and suspenders approach underneath those epoxies. So if you're putting epoxies or things, you can put that silane underneath it, and then, because the epoxies never fail, right? They don't crack or they don't get chipped or scraped. So it gives you a belt and suspenders approach if you're putting silanes underneath your overlays. They're cost effective, they're easy for local crews to apply, they last quite a long time. Silanes stop freeze-thaw damage, silanes stop alkali-silic reaction, and they stop rebar corrosion. It's just a very good tool in your toolbox. So we whipped through that pretty fast because you've been through a lot of those stuff already this morning. So questions?
Tim, I'm going to ask one real quick, if you don't mind. So you said Oklahoma waits a year to put the silane on. I know you don't want to put it on green concrete, but how long is long enough after concrete has been placed?
So the question is when should you apply silane? So typically you need to wait for the concrete to cure down at 28 days. The drier the concrete is, the better the absorption into the concrete for the silane, deeper the penetration. And that's what you want. You want it to penetrate as deep as you can in that concrete. Thanks, Graham.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.